Afternoon session, and we'll continue with Charles in his mini course.
No, I didn't hear. Sorry. Okay, and I was in the course of explaining before the light vanished that this volume function, if you restrict it to the big cone, so by definition this is a space where the convex, a strict convex cone, where the volume is positive. Well, in this open cone is a C1 differentiable. Okay? And the proof of this fact relies basically on two tools, two ingredients. So the first one is Seuss criterion of bigness, which is to say that if alpha and beta are enough classes, then you can estimate the volume of the difference. It's a volume of alpha minus beta. So this is bigger than, so you have to, you can expect that the volume is something like alpha minus beta to the d. Okay, and here the bound is that the volume of the difference is greater or equal to the first two terms of this expansion. So alpha to the d minus d times alpha d minus 1 dot beta. So this is one ingredient. So the proof of this, as I said, is it's not very difficult. It basically boils down to studying a restriction exact sequence, exactly of the same sort as I used last time to check that the volume function descends to the neural survey space. So I'm not going to do that. And the second ingredient is the notion of Neff envelope. So this is where B-divisors enter into play. So here I'm taking alpha to be any big class inside of X. So in the neural survey space of X. And I look at the set of all Neff Cartier B-divisors. So I introduced, whoops. Yeah. I really am trying to be gentle, but it's not really working. Okay, so I'm looking at the set, let's say a P of alpha, which is the set of classes beta, what are Cartier and Neff, and such that beta is less or equal to the Cartier class induced by alpha. Okay, so let me make this a little bit more precise. So what do I mean by beta, a Cartier class? So remember, this is a collection. It means that this is a collection of classes, beta pi, where pi is a proper birational morphism over X. Let's say X pi smooth. So beta pi, whoops, is in the narrow series space of x pi. And to be Cartier means that, okay, so first I have the compatibility under push forward. Which means that if, by any chance, I have two models and the canonical map relating them is a morphism, then the, what is beta pi, it should be the push forward under mu of beta pi prime. So this is a definition of being a Weil class, and to be a Cartier class means that, in fact, beta is determined in some model by some class, and afterwards you only pull back. So there exists maybe, well, pi naught, such that for any birational model that dominates pi naught, beta pi is the pullback of beta pi naught. So here, my notation is like this. You have pi naught over x, x pi, and this is mu. Okay? Okay, so what is this notation here? It's, it stands for the following. So you take your favorite class alpha inside X, and now you construct the Cartier class, which is what? Well, you take the pullback by any morphism, okay, over X. So what is this condition here? Okay, sorry. So this is a Cartier class to be nef. So let me write beta, sorry, as C of beta pi naught, if it satisfies like this, and say beta is nef. The definition is that beta is nef if beta pi naught is nef. And because because nef classes are invariant under pullback, this condition does not depend on the choice of pi naught such that this is true. Okay, so be careful. Be careful. So, yeah, or like this. So, the push forward on nef class is no longer nef. It's just nef in codimension 1. So, if beta is like this and nef, then beta pi is only nef in codimension 1. Okay. What I'm assuming is that it's nef after some at some level, and by pullback, so it's nef for any pi over pi naught. Okay, the last thing I'd like to explain is what is this. So this is a notation. So beta is less than C alpha. It just means that this is less effective or pseudo-effective. So it means that for any morphism, model, birational model, beta pi, let's say C alpha pi minus beta pi is pseudo-effective. Okay? So Joshua explained that, gave a proof that P alpha is in fact filtered, which means that if you take any two elements in P alpha, you can find a third that dominates the two. So fact, if beta 1, beta 2 is in P alpha, then there exists beta 3, if you want, that in P alpha, that is greater or equal to beta 1 and beta 2. So using this, you can show that you can take the supremum of all classes inside P alpha. And so you can define P alpha as the supremum of all classes beta for beta in that space. Okay, so what does it mean somehow? It's so to check this, you need to work in a fixed model. Okay, so you fix a birational model, and then you look at all beta pi for beta in this set. Because of this, if each time you have two of them, you can find a third that dominates the two. But these conditions say that you have to be less than alpha inside pi. So you're in a compact set, okay? And so the supremum like this is going to exist for any pi. Okay. So now I have to use this kind of construction. So, okay, so what is this? We call it the Neff envelope. So if you have a big class, it's a way to extract the best Neff approximant of your class. Okay, in dimension 2, it's quite well known. This is called the Zariski decomposition. And in dimension 2, it's known that this P alpha is in fact Cartier. But when you go to higher dimension, to dimension at least 3, this P alpha needs not be a Cartier anymore. It's really a B-divisor. But so the idea is that somehow you have the cone of big classes, and this P alpha, it's a way to project onto the Neff cone. But the only slight problem that you cannot project onto the Neff cone inside X, you need to go to consider all birational model at the same time. Okay, so there is a, yeah, I excuse you.
Can you also do this when alpha is only pseudo effect?
Yeah, by approximation, but it's you start by defining this for big classes, and then you take how do you say a decreasing limit like this to define by continuity somehow. So, but I think it's well quite essential to have big here. Okay, there is a geometric interpretation of this. Which was given by Couronilla and MacLean. So maybe it was known before, but at least very well explained their paper. So if you suppose that alpha, so here alpha is any class. When I say it's big, it's a real neuron-survey, it's inside the real neuron-survey space. But suppose that alpha is the first-chain class of some big line bundle. Then in fact P alpha is quite geometric. So how do you do this? So you look at the complete linear system that I'm going to write this way, and L. So you look at all sections of L to the power n and the zero locus of this sections. So a complete linear system. And what you can do is to decompose its linear system in two parts. So you see you have a family of divisors. So they might have a common component. Let's call it the fixed part. And then you have another linear system, which might not be complete. Let me call it Mn, which is the, I don't know how you call it in English, maybe the mobile part. So this is a family of divisors, okay? And so in general, it's not, it might have base points, but the base loci of this family of divisor has codimension 2. So you can look at, let's say, the base locus of this family of divisor. This is, let's say, a coherent ideal sheaf, locally defined by the local equation of these divisors. And the point is that now, so the base locus of this guy can be big. It has, in general, it has a codimension 1 part. But if I take this out, then the co-support of this, of Bn, has codimension is small, has codimension at least 2. What? I don't hear you because of the wind, sorry. Support of the quotient OX by Bn. Where it's non-trivial, if you want. Okay, and so this is almost Neff. This is Neff in codimension 1, if you want. So if you want to produce something that's going to approximate, so the class of this guy is something that is very close to BNF and is less than this, well, n times alpha, okay? So it's something that's very close to enter into this thing, except that you need to resolve the base locus. So let's do it. So you consider pi n, let's say, which is any birational model that dominates, let's say, the blow-up of this base locus. And now if you pull back, so let me write this way, n alpha. Well, what you're going to have is that you're looking at the strict transform of this guy. So this is, I should write this way. This is mn prime plus some fixed part that you're going to throw away. And this guy is now, since you blow up the base locus, it doesn't have any, it's global generated, so they don't have any base locus. Base locus is empty. And so what we did here is that we wrote the pullback of n alpha as a class beta n, which is nef, but even better than this, so nef, plus the class here, fn prime, which is effective, okay? So if I divide by n, what I get is a geometric, let's say, a construction of classes, of nef classes that play a role in here. So just by definition, what I have is that 1 over n beta n is less or equal to p of alpha. And the theorem is that, or observation, is that in fact if you take the limit as n tends to infinity of this set of classes, you get p alpha. Okay? So it's a geometric construction for this nef envelope. In the case, alpha is a Fertian class of some line bundle. Here the advantage is that you can work with any class, any real class. Okay, so now I can start the proof of C1 differentiability. I have all ingredients. I have to say, yeah, okay. So when I say I have all ingredients, it's half true because some deep theorem are still missing, okay? So you'll see in a moment, I'm going to use the Fujita theorem. Okay, so what do I want to prove? So again, so alpha is a big class. And maybe gamma is an ample class. So the set of ample classes generates n1 of x. And I want to estimate the volume of alpha plus t gamma. I want to write it as volume of alpha plus t times some linear form, depending on alpha, plus some small, plus O of t, so something that is negligible with respect to t. Something like t squared plus something. Okay, so this is what I want to do. And here it's a bit unclear what this is, right? So I'm going to tell you how to use this nef envelope to define this linear form. Okay, so what did we know? Well, we have this Su inequality. Su inequality tells you that the volume of the difference of two nef divisors is under control. So what I'm going to explain that this gives you a sublinear estimate like this. So we won't have an equality, but an inequality. So how do we do this? Well, we pick beta in this p alpha. So beta is nef now, but maybe in some model, okay? Some model over x. And we're going to, so we want to estimate the volume of alpha plus t gamma. And so the first observation is that since beta is less or equal to alpha, then, okay, so I'm using two things. So, okay, so let me write it down. So this is greater or equal to the volume of beta plus T gamma. Okay, so I might be a bit fast here. So in fact, I interpret beta as a class in some x pi. And here what I should write is, in fact, pi upper star of gamma. But remember that I checked that the volume is invariant under birational transformation in the sense that the volume of alpha, this is the same as the volume of the pullback by alpha. Okay? So here, if you want, what I should write is something like beta pi plus pi naught plus something like this, where beta is the Cartier class associated to beta pi naught. But just to simplify the notation, I'm going to write like this, volume of beta plus T gamma. Okay. So now beta is nef, and I assume gamma ample, so nef. So then you have two cases, right? Either T is positive, but then the volume is just beta plus T gamma to the power D, or T is negative, and then you don't have an inequality, but you have an inequality. So you can use U inequality. So in both cases, what you get is something like beta to the D plus T D beta to the D minus 1 times gamma. Okay, so let me write it down here. Okay, so the volume of alpha plus T gamma is at least beta to the D plus T D beta dot gamma. Okay? So this is for any beta inside P of alpha. So now what is natural to do is to take, so this is true for any beta, so let's take the supremum. Okay, so I'm going to take the supremum over all beta inside P of alpha. So let me state a definition. So I'm going to take the supremum of all these beta D, so these are non-negative real numbers. And the point is that if beta is less or equal to beta prime, since beta is nef, so beta and beta prime are nef, to check that beta to the D is less or equal to beta prime to the D. So one way to see this is like this. So you have beta D times. Okay, so they are all nef. So this is less or equal to beta prime dot beta D minus 1 time. Okay, so replace this by ample classes and go to the limit if you want. And then you use the same trick each time for beta replacing by beta prime. Okay, so what it means that, so you can check it's bounded also. So so this is finite. So let me define P alpha to the D as this number. Okay, if you want, so the sup of the beta is this nef, this Vi class P of alpha, this nef envelope. So I'm going to define P alpha to the D as being this supremum. So I declare this. So yeah, maybe it's just a simplified notation for the moment, but then I'm going to develop later on like the general theory of intersection of nef classes. And I'm going to do the same here. So here I forgot D minus 1, I guess. So I'm going to define P alpha D minus 1 dot gamma, again as the supremum of this beta D minus 1 dot gamma for beta in P of alpha. Okay, so here again I use the fact that gamma is ample, and so this supremum is increasing when the beta is increasing towards P of alpha. Okay, so this is again a definition. And the point is that, so this is, so if gamma, so you get a linear form from N1 Rx to R. So here I'm a bit, I'm not sure if I'm a bit sloppy, but so with notation, so gamma, I'm intersect this with PD minus 1. So if I want to be very careful about notation, here It's a class in N1 of X, and here I'm intersecting with a class which is a Cartier class, okay? So I should write something like this, but yeah. Okay, so now, so we are almost done. So let's look at this inequality here and take the supremum. So take the sup over all beta in P alpha. And so what you get is volume of alpha plus T gamma greater or equal to, okay, P alpha to the D plus T times D P alpha D minus 1 dot gamma. Great. Now here is the main, one of the main theorem, key theorem, called Fujita's theorem, is that in fact this top intersection, so P alpha to the D, it turns out to be the volume of alpha. Okay? So I'm going to discuss this later on, so let me finish the proof. It's almost one line, so the volume is greater or equal to the volume of alpha plus this thing. So let me call it L alpha of gamma. Maybe not. Just this. And now there is a standard trick. So you have a sublinear estimate. So you play the same with the volume of alpha, but on the other side. So volume of alpha. I'm going to cheat a little bit, but I cheated so many times that I don't think this is a big deal here. So alpha is alpha plus T gamma minus T gamma. Aye. Great idea. And now you use exactly the same estimate, but for this this difference here. So it's greater or equal to volume of alpha plus T gamma. And if you're a little bit careful, this is, sorry, minus T D P of alpha plus T gamma to the D minus 1 dot gamma. Okay, so you have volume of alpha plus T gamma with greater or equal to something nice. And here you get the reverse inequality, except that, so you have to be careful because this is not exactly P of alpha to the D minus 1. But so it's not difficult to see that P of alpha plus D gamma D minus 1 convert to P alpha D minus 1 because alpha is big. So I just claimed this. It's not really difficult. And so in the end, what you get is you get an upper bound for the volume of alpha plus T gamma, which is less or equal to the volume of alpha plus T, well, D times P of alpha plus T gamma D minus 1 gamma. And this is, because of this, this is the volume of alpha plus this thing plus small o in T. So if you swallow or if you accept everything I said, this proves the differentiability. It's differentiable at alpha, which is big. And in fact, it's not only differentiable, the differential is this thing, and so it's in fact continuous. It's plus L alpha is continuous. So which means that volume is C1. So in fact, we used in here, so this is the statement here. So the fact that you have the continuity like this is exactly saying that the differential is continuous. Okay. So let me discuss now this Fujita's theorem, which needs to be the key statement here. And then I'll discuss some consequences of this C1 differentiability. Yeah, so basics of Fujita's theorem. Okay, so I don't know how many approaches there is to prove this, but one approach, so it's due to Lazar's field and I think Lazar's field. And so they use the multiplier ideal sheaves. And Nadal vanishing. So I cannot say it's completely trivial. There is a more direct approach due to Lazar's field Mustatsa. So sorry for the spelling. And this is based on Okonkov bodies. So if you want this, so what does it say? It says that, so remember what I did is that I was looking at the complete linear system and splitting them in two parts, pulling it back to a resolution of the base locus of the Mn. So what it says is that, in fact, this thing, which is globally generated, in fact, catches most of the number of sections of this guy. So in other words, so H0 NL divided by ND multiplied by this, it's approximately the same number here. So what can I say? It's, maybe divided by n to the d. Okay, so one more comment before I turn to this the development of intersection of NEF B-divisors in general. That we can look at the volume of 1 plus T alpha. Sounds stupid, but you look at volume of alpha plus in the direction of alpha, okay? So we know that this is homogeneous, so this is 1 plus T to the D, volume of alpha. But on the other hand, the theorem tells us that this is the volume of alpha, okay, so P of alpha to the D, and plus T times D times P of alpha D minus 1. Dot, so before it was the gamma now is alpha, dot alpha, plus small o of t. Okay, so here is, this is P of alpha to the D. So if you compare these two things, what you get is the following equality. P of alpha to the D is equal to P alpha D minus 1 dot alpha. Okay, fine. So if I put alpha on the other side, or on this side maybe, because I know that alpha is greater than P of alpha. So I get P alpha D minus 1 dot alpha minus P alpha is 0. Okay, what is this? So now pick, so this is some kind of orthogonality statement, right? So this is a curve class, Weil class, and this is a divisor class. So let's go down to D equal to 2 and look at Zariski decomposition. So what does it say? It says that if you have, let's say, an effective class, effective divisor, then you can decompose it in terms of as a sum. So usually, I think the notation are P plus N. So it's kind of strange. N is not nef, it's negative. Okay, but so P is nef, and this guy is the support of this guy is contractible, and N is effective. And one of the important conditions on the direct decomposition is that, in fact, these two things are orthogonal. And so here what I'm claiming is that, so what we did here is to extend this kind of, this Zariski decomposition to higher dimension. So this decomposition here lives inside X. You don't need to consider birational models over X, etc. In dimension 2, you can only play directly inside your favorite projective surface, okay? Starting from dimension 3 on, you need to go you need to consider B-divisors. And so this claim here is exactly this. So alpha, maybe D is alpha, P is P of alpha. And what is N? This is exactly alpha minus P alpha. Okay. So these two things are exactly the same. Okay, so yeah, I'm done for the differentiability of the volume. And now what I'd like to do is to define what is in general an F B class, and to use this to develop some intersection theory of Nef B class in general, and to deduce from this some kind of duality statement. Okay, so maybe if there are some questions or anything isn't clear on that part. No, okay. Then I try to be more, if time allows, I'll try to be more dynamical tomorrow, but we'll see. Okay, so the aim now is formalize the notion of Nef B class. So what I'd like to do is, so what I know is what is a Cartier B class. So again, this means that alpha is the Cartier class attached to alpha pi naught for some pi naught, and alpha pi naught is Nef. Okay, so before I define in general what is a Nef Vi class, I would like to make two comments. So the first I already did is that alpha pi is not Nef in general, well, except in dimension 2, but it is Nef in codimension 1. And the second thing I'd like to mention is a consequence of negativity lemma. So what does it say is this negativity lemma? So I'm not going to state it in full generality, but so suppose that you have a birational proper morphism, x pi to x, and suppose that you take a class here, let's say beta, which is Nef. What you can do is push it forward to x and pull it back to x pi. And the negativity lemma tells you that when you push forward and you pull it back, you get something which is bigger. Okay, so the push forward, the pull back of beta is in fact greater or equal to beta. So again, this means that the difference is pseudo-effective. Okay. So the proof, in fact, did you do it or no? Okay. So the indication is that you reduce to dimension 2 by slicing by hyperplane section. And then you use Hodge-Index theorem. It's a nice exercise. Okay, so let me translate this negativity lemma to a property on the Cartier Nef class in general. So if you use this, so we are going to use it for pi equal to this pi naught, okay? And so what it says is that, so what is the push forward under, the push forward by pi of my class here? This is, since this is by definition, this is going to be alpha pi, or alpha inside x. And what is the pullback here? I'm considering the Cartier class induced by this guy. Okay, so if I translate this negativity lemma into this language of B-divisor class, what this means is is follows. So let's take pi prime that dominates pi. Okay, so yep. What's the deal? So you take, okay, alpha is Cartier and Neff. So what you can do is you can look at alpha pi, which is a class in N1 of x pi, and you take the Cartier class induced by this, maybe pi prime, and the same here. And the claim is that when you go up in the tower, in fact, the set of Cartier classes are going down. Okay, yoga of B-divisors. Okay, so it's not, I mean, it's like it's really translation of this property in terms of B-divisor classes, okay? So this is something I'm going to use. So again, what does it mean? It means that if you have an F class, you start from some class, and then going up in the tower, you can approximate this by a sequence of Cartier classes. In fact, it's going to decrease to alpha. I hope I'm not mixing up the inequalities, but I think it's fine. Okay, so now let's define. Let's define in general what I mean by an F B class. Okay, so should not start this way, but so the first observation is that the set of Cartier classes that are Neff is a convex cone in, well, okay, fine, in the space of Cartier classes for sure, but also in the space of Weil classes. And remember that, that this space is endowed with a canonical locally compact topology, okay? So remember that, so here you have a topology, locally compact. And so I'm going to define the cone of Neff classes inside of Weil Neff classes as being the closure of this set. So this is a closure of, so you're going to love it. So let me write down what this means in practice, okay? It's quite, let's say, intricate. So, okay, so what does it mean for a Weil class to be Neff? It's quite intricate, okay, because the set of all birational model is huge, okay. Some good cases, it's if you're working over Q-bar, it's countable, but in general, it's even uncountable. Okay, so what does it mean? It means that if you fix any birational model, pi, then you can find a sequence. Then there exists a sequence beta n of what? Of Cartier, of nice class, okay, of Cartier classes that are Neff, such that what? Such that if you look at beta n in x pi, this is going to converge to alpha pi. So beta n pi converges to alpha pi. It's really tricky. Okay, so what we would like to have is somehow to find a sequence of that would be very nice to have a sequence of Cartier Neff classes that converge directly to alpha. But this is not how you start. You start like this, so that this cone, it's so one of the very important property here is that if you mode out by, let's say, scaling, and you endow it with the canonical topology here, this quotient is going to be compact. Okay, so let's say that if omega is an ample class in N1 of x, then you can look at the space where alpha or nef and normalize them such that, so remember that you can always intersect any Weil class with a Cartier class, it's no problem. So you scale this alpha such that this normalization holds, and then in fact, this is compact. So we're going to see that this is something very important in application, okay? So this is why we start with such a difficult or not amenable definition, okay? So before I state the main theorem, so the main theorem is that, in fact, these classes are, let's say, approximable by Cartier classes. So in fact, you can permute the quantifier. So there exists a sequence. So if you have an F class like this, there exists a sequence, in fact, of Cartier F classes decreasing to alpha. This is an essential theorem. So before I explain this, let me give examples of such class. So we don't know that many examples. But so we have Nef Cartier classes, of course. Well, beta Nef class, you take beta n equal to beta, and it's working fine. And if alpha is big in any model, let's say in X, also P alpha is Nef. But now this time this is okay, so this is essentially by definition because alpha, let's say, is the supremum of things. But now the point is that recall that in general, so here alpha is it's a class in N1 of X, but this guy is no longer a Cartier in general. Okay, so there are some examples where P of alpha is really a Weil class. So this may not be Cartier in general. It's hard to construct counterexample actually, but it exists. Yeah, you have a question on your face, so.
I don't understand. Maybe you said in which sense you take alpha intersect with omega.
Okay, so what does it mean? So here, alpha is a collection, so it's a Weil class, so it's a collection of classes, right? By definition, what I mean by this is, in fact, I compute this directly inside X. So if you want, this is alpha in X dot omega d minus 1. Okay, so you can check that if this is Nef, this guy, if this is 0, in fact, alpha has to be 0. I didn't explain this, but so if you scale this is somehow, this is a slice of your closed convex cone. And it's not difficult to check it's compact. Maybe I'm cheating too much here. Maybe I should say this. Okay, well, okay, fine. Let me put this way, and I'm probably making a small mistake, but it's not so important. Okay, and so last thing, so many examples come from dynamics. So the organizer are not very happy with me because I plan to, in the title, I put application to dynamics, and there are no dynamics at all for now. So I'm going to explain a little bit more tomorrow, but Susanna talked a little bit about this. She talked about, at the end of her talk, she said that you can consider like an infinite dimensional hyperbolic space and so on. And in fact, this infinite dimensional hyperbolic space, it contains these Nef classes. So it's, anyway, so let me, in one line, so if you have, let's say, a birational map, let's say a birational for P2 to itself, birational. So it's a map in homogeneous coordinates which is given by homogeneous polynomials without common factors. And let me denote their common degree by a degree of f. So of course, if the degrees are 1, it's not very interesting. Dynamics is essentially linear. So I'm going to assume that degree is at least 2, even more. So I let you check that the sequence of degrees has a nice property to be submultiplicative. So if you look at the degree of the n plus mth iterate, this is less or equal to degree of fn times degree of fm. Okay. So if you have this, then you can define the, so using the Fekete lemma, you can define lambda 1 of f, which is the limit of degree of fn 1 over n, which is at least a number at least 1. And so this is called the dynamical degree. And when the dynamical degree is 1, I'm not happy in the sense that dynamics is too easy. And so I want to assume the dynamical degree to be larger than 1. So if this happens, and there are many, many cases where this happens, most of the time it happens, then in fact you can construct there exists a unique Neff class over P2, so here X is space over P2, such that, so I didn't define it, but the pullback, there is a natural way to pull back Neff or B-divisor classes, such that this class is multiplied by lambda 1. Okay, so then you can do the same. So if F is birational, in fact, lambda 1 of the inverse is the same as lambda 1. So you can do the same construction, but for its inverse. So you also have a class, so this class is unique, well, okay, up to scaling. So you have a class theta minus, which is Neff, and again, so such that the pullback by F minus 1, so this is a push forward, theta minus is lambda 1 theta minus. Another thing is that in most cases, these two classes are not Cartier. Sometimes they are, but you have a fact or theorem is that if theta plus and theta minus are Cartier, then F, so F is not really an automorphism because if it were an automorphism of P2, it belongs to PGL3 and the dynamical degree would be equal to 1, okay? So, but if these two classes are Cartier, in fact, what you can show is that you can blow up P2 at some point such that F lift as an automorphism. And F lift as an automorphism of some rational surface over P2. Okay, so I'll come back to maybe not exactly this kind of theorem, but so I'll come back to this dynamical degree stuff tomorrow. Probably try to explain you how you construct this kind of classes. Okay, so here I just wanted to mention that these classes arise very naturally in dynamical context. And in fact, this was one of the reasons to introduce B-divisors and so on, and to look at Neff classes. Okay. So here we have learned a lot about Fano varieties, but here you don't want to look at Del Pezzo surfaces because automorphisms are too simple. Okay, the dynamical degree is too easy to understand. And so here there are rational surfaces for which there exists an automorphism of dynamical degree at least 1, greater than 1. you need to blow up P2 at least 9 points and even more, okay? So you're far from being Fano. Okay, so let me check. Okay, half an hour. That's yeah. Sorry?
33 minutes.
Whoa. Okay, so let me state the main theorem. So let me come back to this notion of Neff classes. So the aim is to develop intersection theory of Neff classes, and then to deduce from this some duality statement. Okay, so I hope the duality statement are going to be nice. We'll see if I manage to get to this today. Okay, so theorem. Take any alpha, any Neff B class. So yeah, so it's a theorem by Deng and myself a couple of years ago, and can be obtained also, or it was obtained by Buxom and Johnson, let's say at the same time. So the statement is that there exists a sequence, let's say alpha n, of Cartier classes, which are Neff, and which are decreasing to alpha. So it's really non-trivial, right? So because so from this definition, basically you have to switch to permute this quantifier. So there exists such that for all pi, something like this exists. Okay. Yeah, half an hour, yeah. I'm thinking whether I should discuss the toric case or not. Let me explain briefly. Okay, so I'm not going to give the proof of this, but the just some indication. So the first thing that we do is to reduce to the case where alpha is the Neff envelope of some guy, or some beta, which is big, inside some x pi. So in the case where alpha, so what I said is that if alpha is a Neff envelope of something, then it's clear that, it's Neff in the previous sense. But be careful that the Neff envelope is defined as a supremum of Neff character classes. So here it's a bit strange. We want something like this decreasing, okay? So it's not completely obvious from just looking at if alpha is a Neff envelope that this theorem is actually true. Okay, and in fact, so in that case, it's the same kind of techniques that are used to prove Fujita's theorem. So it boils down to nodal vanishing. So we use, in that case, we use again the technology of multiplier ideal sheaves. So how do you reduce to something like this? Okay, so you fix, let me fix some notation. So yeah, okay, so omega is any impulse class inside X. You fix pi, any birational model. And you fix epsilon very small, positive. Okay, so what you want to do is, so you want to construct a sequence decreasing to alpha, which is Neff and Cartier. I'm going to construct a family parameterized by this pi and epsilon of envelope of big classes that are decreasing to alpha. And now if you know the theorem for envelopes, if these NF envelopes are decreasing to alpha, this gives you the theorem here. Okay, so what are the envelopes I'm going to look at? So let me, so let me look at, so alpha of pi and beta. So what I'm going to do, I'm looking at alpha pi, I'm adding epsilon omega, and I'm taking so I'm looking at the Cartier class induced by this, I'm taking the NF envelope of this. Whoa. And so the claim is that so it's kind of natural thing to do, right? So you have alpha, which is NF, then you stop at some fixed level. Okay, maybe it's not big, so taking the envelope is not nice, so this is why I'm adding like a small ample class. So now it's big. Okay, I'm taking the class there, the Cartier class, and then I'm taking the NF envelope. Okay, and the claim is that if you go up, so if pi prime is go up in the tower, and if epsilon prime go down, then in fact this classes is decreasing. So alpha pi prime epsilon prime is less or equal. So okay, so it's greater or equal to alpha and less or equal to alpha pi epsilon. So if you let epsilon tends to 0 and pi tends to infinity, whatever that means, what you get is this. So it's not exactly a sequence, but a family of NF envelopes that are decreasing to alpha. If you believe in this statement here, then you can have, it's not exactly a sequence, but the net of NF Cartier classes decreasing to alpha. And then there is an argument which is non-trivial to extract from this net actually a sequence that is decreasing to alpha. Okay, so if I try to prove this in details, I'm sure I'm going to screw up all the sign and so on. But this is, so the fact that this is decreasing in epsilon, or increasing in epsilon, I should say, is clear, because if you increase epsilon, then alpha pi plus epsilon omega is going to increase, Cartier class is going to increase, and the NF envelope is going to increase. Okay, and now, so let's fix epsilon. So what's happening if you replace pi by pi prime? When you're going up, forget about this. You look at the Cartier class of alpha pi prime. By the negativity lemma, you're going down. The NF envelope is going down. Okay, and the fact that this is greater or equal to alpha is not difficult. So this is negativity lemma. Okay, so now intersection theory. Okay, so I'm going to use, it sounds, I understand it sounds a bit technical. Why are we playing with these kind of things? Okay, and so I'm not sure the definition I'm going to make is going to make all this very transparent, but I'll make some comments on the analogy between the intersection theory I'm going to describe and what's happening in complex analysis. Okay, so if you take alpha 1, let's say alpha d, NF classes, so X is of dimension d. Then we're going to define the intersection number alpha 1 alpha d as a non-negative real number. Sorry, maybe I need to be a little bit more general. So let's say alpha k, k less than d. So I'm going to define this, and this is going to be some numerical class in codimension codimension K. And the way I do this is, so what I know is that I can intersect Cartier classes, okay? Vi classes is harder. So in order to define this, I'm going to define this as a limit. So, and the limit of what? Well, I'm applying for each of these Neff classes, alpha 1 to alpha k, I'm applying this theorem. So choose sequence alpha I n decreasing to alpha I that are Neff and Cartier. And consider this intersection number alpha 1n, alpha 2n, alpha kn. So this is a Cartier class of a numerical class of codimension k, which is, since all these classes are Neff, in fact, it's pseudo-effective. Now, the point is that each time you're decreasing one of these guys, then the sequence is going to decrease also. So this sequence is decreasing to some class I'm going to define as being this class. Okay, decrease to alpha 1, alpha k. So when you do this, there is one small problem, is that this theorem does not give you a canonical approximation of alpha. Okay, so you need to check that if you choose any other sequences of Neff Cartier classes decreasing to these classes, then this converts to the same thing. So you learn that my game is to put everything I don't want to explain as an exercise. So you need to check. So this is not difficult, to check that this definition does not depend on the choice of approximation. Okay, basically it boils down to, okay, you can assume that alpha I are in fact big by approximation, and and here what it means that if you have a sequence decreasing to alpha I and have another one, then the other one is going to be less than some alpha I n for enlargement anyway. So playing with this, you get exactly the fact that this does not depend on your choice of approximation. Okay. What are main properties of this intersection product? So it's multilinear. Okay, it's not clear. Okay, what does it mean? And it's Neff is the Neff. It's a cone. Okay, so if you take any two classes, alpha 1 prime, so alpha 1 plus alpha 1 prime dot alpha 2 alpha k, this is alpha 1 alpha 2 alpha k plus alpha prime 1 alpha 2 alpha k. Okay, this is symmetric. Yeah, it's non-negative, I should say. So alpha 1 alpha k. When I say non-negative, it's okay. If k is equal to d, this is going to be a non-negative real number, but otherwise it's pseudo-effective. So it coincides with the usual, with the intersection product of Cartier classes. And also, it coincides with the intersection product I defined for Neff envelope. So it coincides, so it's compatible with what I denoted by P alpha to the D and P alpha D minus 1. Okay, if alpha is a big class inside X, so inside some X pi that I defined before. Yeah. Okay. So now this intersection product is quite subtle to manipulate because so remember that nef is inside, it's a closed cone inside the space of numerical classes, and you have a canonical locally compact topology in here, okay? So you might wonder, okay, is this intersection product continuous? So this is not true in general, so you have to be very careful. But what is true is that if, so this kind of statements remains true. So if alpha in is a sequence of nef classes that is decreasing to alpha I, then you have convergence. So if you want, so here this was a definition, okay, and the classes were Cartier. So what I'm saying here is that now replace this by any decreasing sequence of nef Vi class, then this convergent is still satisfied. In general, if you only assume that you have, let's say, convergent like this, then you don't have equality, but what you can check is that the lim sup of these guys is less or equal to alpha 1, alpha k. $16 minutes, right? Yeah, okay. 6.5, well, let me wait, now 16. Okay, so I'm not sure to, I'm making an observation here for those who are familiar with intersection of positive closed 1-1 currents, so probably not so many of you, but so in fact, the definition of this were inspired by the intersection of positive closed 1-1 current. So let's say in complex analysis. So these continuity properties are reminiscent or analogous to continuity properties of intersection of positive closed 1-1 current. So somehow for me it was not completely surprising that you don't have like so many good continuity properties, okay? So I cannot really say that there is a direct connection between the two theories, but still. Okay. Okay, so now I wanted to give some application to duality problems. Wow. I'm not that fast. Oh, to duality. I think it's kind of nice. Okay. 15 minutes. Let me try to do the following, okay? I'm going to state something. I'm not going to explain, then try to describe what is the statement in Algebraic geometry. And then tomorrow I'll start with proving this statement. So the theorem is something like this. So I won't define all terms right now, but you have so I define this closed convex cone. And then you can define an analogous cone, which is in C of curved classes. And so if you look at this map, alpha goes to alpha d minus 1. So alpha is an F class, as defined here, you can look at its d minus 1 power. So what I'm claiming here that this you arrive in some cone, which is a cone of curves that have nice positivity properties. Okay, I'm going to discuss this tomorrow a little bit more. And this is a bijection. Okay, so what I'm going to do tomorrow is to prove this. Well, explain. So we know what this is. So big means that the volume of alpha, or alpha to the d, is positive, and so I have to define this part. Okay. So what I'd like to do is to describe the toric situation, the toric version of this statement. It's kind of nice because it's the toric statement of toric version of this statement is in fact Minkowski's theorem. Okay, so let me explain it. Toric situation, toric version. Okay, so what is Minkowski theorem? Okay, there is a lot of Minkowski theorem. So you consider a polytope, convex polytope. Let's say P in RD. So P is a convex hull of finitely many points. Okay, and I'm going to assume that the interior of P is non-empty. Okay, so I have difficulties to draw polytopes in higher dimension. I don't know. Okay, well. Yeah, something. Okay, so let me assume that the point 0 lies in the interior of P. Okay, just translate your polytope so that this is true. Okay, so now when you have a polytope, you can look at its codimension 1 faces. Okay, so you look at the faces, let's say Fi, like this, codimension 1. And for each face, what I can do is I can look at its normal direction, normal unit vector, like this. So I have to choose, there is the convention here, I have to choose either the inward, so toward the interior of P, or outward. Okay, I'm going to make the convention that this vector is pointing outward. Okay, and so Vi is the normal vector to Fi pointing outward. And I'm going to assume that the length of Vi is given by the, okay, so I have here Rd is ended with a Euclidean metric. And I'm going to let the norm of Vi to be the area of Fi. So the length of Vi is the area, okay, I should not say the area, d minus 1-dimensional volume of Fi. Okay? Good. So now I have a map from the space of polytopes to the space of, to the set of vectors. Polytope P. Let me call it V of P, which is this collection of Vi. Okay? So there is one thing is that in fact, these VIs, they satisfies one condition, is that the sum of the VIs, I don't know why I'm putting arrows here, but just to emphasizing that this is a vector probably. So the sum of the VI is equal to 0. So this is a consequence of Greenhouse-Trotsky, or if you want, so what you do something like this. So let's say in dimension 2. Yeah, so you take any direction V, so any unit vector V, and what you do is you look at the orthogonal projection. So let me do it with my hands. So you look at the orthogonal projection onto, you look at the orthogonal projection onto a plane orthogonal to V. And now what you do is you compute, so you have two set of faces. So you have the faces for which the vector Vi intersect V positively. And then you have the other ones. So maybe you have the blue and the pink, right? Yeah, well, okay, anyway. And so if you look at the projection of this, of the area of all these faces, then the projection of this and projection of that, of the blue part and the pink part, it should be the same. And if you do this, what you get is that the sum of Vi scar of V has to be equal to 0. Great, but this is true for any V, so you have this condition. Okay. So now the theorem of Minkowski tells you the converse. It tells you that if you give me any finite set of vectors Vi such that sum of Vi is equal to 0 plus, okay, there is another condition here, is that I want the interior to be non-empty, so I don't want the Vi to lie in a codimension 1 plane. So condition 1 is this, is that, and they generate RG. So the theorem is that conversely, if you have a collection of vectors such that the sum of Vi is equal to 0 and they generate RD, then there exists a unique polytope up to translation P such that V of P is equal to Vi. Nice. So I like very much this result, right? So nothing is trivial here. Okay, so in the remaining 5 or 4.30 seconds minutes, I'd like to give you a hint why this theorem is the same as this one. It's exactly the same. In fact, if you translate this one using Algebraic geometry, you get back exactly Minkowski's theorem. So if you want, this is as hard as this one. In fact, the proof of this, we're going to use an idea to prove this theorem by Minkowski, which goes back, so if I remember right, to Alexandrov, and which uses variational argument. So it's kind of nice. And so just one more thing is here, of course, you can extend this result, not only, so here we're playing with polytopes, but there is also some results where you replace polytopes by convex bodies. For instance, if your convex body is smooth, then what you get here is some kind of measure, smooth measure on the sphere, etc., and so on. Okay, and so you get back to Yau's theorem. Nice. Anyway, so what is the connection between the two? 5 minutes. Okay. So in toric geometry, so you take let's say a projective toric manifold. of dimension D. So this is given by some fan. So I think people, okay, I use delta, so some people use sigma, but so this is a collection of cones inside RD, so convex, polyhedral, rational cones, so on, satisfying some compatibility condition. And so what is the space of, well, N1 of, let's say, X of delta? In fact, it can be interpreted as the space of piecewise linear function with respect to this fan, modulo linear functions. So modulo linear functions. Okay, yeah, okay. And a class is nef. Is the same as saying that, so the function which is attached to this guy, let's say H alpha, is convex. So now when you have a class which is nef and big, so you have a convex function, and so you can define a polytope, P of alpha, which consists of all linear functions. So, okay, so when I say H alpha is convex, it's also one homogeneous. So you can look at P of alpha, which is the space of linear forms, which are less than H alpha. So this is a polytope. Okay, so I'm not going to describe, so if I have a polytope like this, so you cannot, okay, what is this self-intersection here? Well, anyway, I'm probably over time, so I'm just going to tell you, okay, why a set of vectors gives you something like an element in nd minus 1, etc. So if you have a set of vectors in Rd, such that sum of the VI is equal to 0, I want to define something like a curved class. So by dualities, this is something, if you give me a piecewise linear function like this, I should give you a number. Okay, so what you do is that if you have H, which is a PL function with respect to delta, you look at the sum of the H of VI. But be careful here. So the classes here is a piecewise linear function modulo linear functions. So if you want this to exist, you really need to this condition to be satisfied. Okay. Okay. And then so now I think my time is over. But what I'm saying is that if you read this by looking at not all birational models over your favorite project toric manifold, but only toric birational models, and then you use this theorem, you get back exactly that statement. Okay, so tomorrow I'll start with indicating how to prove such a thing using variational principle, and then I'll try to give you more examples in dynamics of how to construct nef classes. Okay, thank you.